Hey guys, welcome back to another low-level learning tutorial. Today we're going to be going over memory operations in x86 assembly. By the end of this, you should be able to do the following. Push a string onto the stack and write it to standard out, and then write a string to the stack using store operations and write it to standard out as well. If you didn't watch my previous video, it's going to be a little over your heads. I would go check that video out. I'll drop a link in the description. That's where we learn how to move data in and out of registers and invoke a system call to get the kernel to perform a function for us. So to go into this tutorial, we need to first talk about memory in assembly, right? In a program, typically you have this memory structure that's referred to as the stack. And you can think of it as a stack of plates, right? And that represents the memory that you have access to when you're writing your program. And that memory lives in RAM, random access memory. In my diagram here, so this is going to be a little much, but just understand that the data grows down positively, right? So as ESP goes up, as we push onto the top of the stack, ESP gets decremented. And the width of the stack is the word size of the architecture, right? So in this case, we're doing 32-bit Intel, right? So the word size for this stack is 32 bits or 4 bytes, right? So for example, the value 1, 2, 3, 4, 5, 6, 7, 8 in hex, which is a 4-byte value, can live on the stack as a single word, right? So when your program starts, you have ESP, which points to the top of the stack, right? And as you push, you execute the push instruction, ESP gets lower by 4 every time. The stack gets taller, and your data goes onto the stack. So what we're going to do is we're going to write a little program that pushes something onto the stack, and we're going to print it out to the screen, right? This is going to be our first exposure to writing data to the stack. So let's execute the push operation, right? So push, and we're going to use this value, and I'll explain why we use this value in a little bit. 0, 0, 4, 3, 4, 2, 4, 1, right? So after we execute that value, the top of the stack is going to have this value in it, right? It's going to have 0, 0, 3, 4, 3, 4, 2, 4, 1. Awesome. You may be asking me, why do we use that value? That value is important because it actually equates to the string A, B, C. You may be asking, how does a number become a string? Okay, well, in computers, all data can be interpreted in different ways, right? So an integer can also be interpreted as a string if the values are ASCII printable, right? So the value 0, 0, 4, 3, 4, 2, 4, 1 in little endian is actually A, B, C null byte. I said little endian. What does that mean? So in Intel is a little endian architecture, right? Little endian means that when you're doing a memory store, the least significant bit, or the LSB, the least significant byte, or the LSB, gets stored first. So 41 is A in hex, so that gets put onto the stack first. 42 is the next most significant byte, that gets put on the stack next, and so on and so forth. So the integer OX 00434241 is actually the string A, B, C null byte. Cool. So what have we done? We've pushed that value onto the stack. Next, we need to invoke the system call, right? So if this value lives on the stack, we need to set up our system call. So what was the syscall number for syscall write? If you watch my previous tutorial, you remember that syscall write is system call 4. Next, we need to make EBX equal to the file descriptor we want to write the data out to. If you watch my previous tutorial, you'll know that EBX needs to be 1 because 1 is standard out. And now we need to make ECX equal the pointer to the thing that we want to print, right? So if we pushed our string, what is the new pointer that exists that already points directly to our string? Well, we talked about this before, right? If we look at this operation, if we've performed a push, ESP will point to the top of the stack where our new push data lives. So after we execute that push instruction, ESP will point to it. So if ESP points to the top of the stack, we can then move ESP into ECX. So now both ESP and ECX point to the string we want to print out. And then finally, we set EDX equal to the number of bytes we want to print, and that is going to be 3. We can do 3 or 4. I like 3 currently. And then finally, we invoke the syscall, right? And I made a little make file that makes things easier for you. Basically, you type make, and it runs the instructions I told you about in the previous tutorial. So if we run make, we see the make file is putting our program together for us, and then it runs the program, and we do print ABC to the screen, right? To make this a little prettier, we're going to change our null byte in our code to OX0A. That's the new line character, or the character that happens when you press enter. It'll just make our flow a little cleaner. So we need to make the null byte 0A, and we need to make EDX equal to 4 to actually print that 0A. So we type make again, boom, ABC, cool. So what have we done? We pushed a string to the stack. ESP, after that push instruction, pointed to our string. Then we made ECX, which is the register that needs to contain the pointer to our string, come from ESP, which already points there. And then we called the syscall. ECX pointed to our string, and we printed it to the screen. Awesome. That's one way of doing memory operations in Intel, right? We can push things to the stack. Another way is doing a direct memory write. So instead of a push, which pushes get kind of messy, right? Because what did I say? Every time you execute a push instruction, ESP is getting less and less, kind of without you knowing about it. If you don't keep track of that, that can get pretty messy pretty quick. So another way we can do this operation is, instead of pushing the data there, we can do a memory move. So normally we've been doing moves like this, right? Where like EAX becomes 4. Well, there's a new way of doing moves where instead of moving to ESP, we wrap it in these hard parentheses. And what that actually is saying is that don't move into ESP, the register, move it to the thing that ESP points to, right? So instead of treating ESP as a register itself, we treat it as a pointer, and we move something to where that points. So, and we're going to move exactly what we said before, move 0A, 43, 42, 41, which is the string ABC new line, little endian, right? So we're going to compile this. We're actually probably going to get an error, right? So the error here is ambiguous operand size for move. So what this is saying is that we're trying to move something where ESP points to, but the assembler doesn't know how big the thing is. We all know how big the thing is. The thing is 4 bytes. But when it actually assembles the instruction, it needs to know the max width of the operation, and we're not specifying that. So the way you specify that in Intel assembly, Intel syntax, is going to be by adding move dword pointer. So what that's actually telling the assembler is to treat ESP, the pointer, as a pointer to a dword type. And in assembly, a dword, because of historical reasons, ends up meeting a 4-byte wide memory structure, right? So what we're saying is move to the thing pointed to by ESP of size dword this value, which is a string A, B, C, new line. Then the rest of our operation, right? Move into EAX, the value 4 for the write syscall. Move into EBX, 1 for standard out. ESP points to our string, so move that into ECX. Move into EDX the length of the string, and invoke the syscall. We type make. Oh, I didn't actually save. And type make. Cool. And we get ABC to the screen. Anyway, guys, I hope that made sense to you. Thanks for watching. Drop a like, subscribe. I drop content like this all the time. And leave a comment on what you want to learn next. Thanks for your time. Bye-bye.